taking square roots. And again, doing these things, it's not easy, right? What's not easy about this thing, first of all, you got a decimal now, and kind of looking at it, it becomes difficult, all right? Now, before I go over it, what I'm claiming over here is that if you do the algorithm, one of the things you may want to do is convert this number to a whole number, divide it by some power of 10. Right now, if you did that, some students will actually do that. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I count that right? Let's see, 1, 2, 3, 4, 5, 6. Yeah, 10. So you could write the number as 631 38916 divided by 10 to the 10th power. All right, the square root of 10 to the 5. All right. And then you're left with a number like 63, and you're left with a number on the end, which is 16, and you start to think about how you could come up with those. All right. Now, again, it all depends on a binomial expansion, starting with something, trying to match. So if you think about matching, and what do I mean by this over here? Let's see the number we're at. We're at 63, right? So, like if I said 7, that would be 49. If I said 8, 64. Well, 8's too big, so I'd go with the 7. All right. Now that's what Wells does. He starts with the first one, so he'd start with the 7, and then he'd expand with this over here. I find it painful. It's difficult to get through that. It really is. All right. But he does it over and over again for polynomials. And then he starts using numbers. All right. What I'm going to do, though, is I'm actually going to use Sage to do the square root of that. Let's go back over here. SQRT. And what's the number? 0.0063 138916. Now, the people coding Sage are quite good at this subject area. Right now, when I say coding Sage is based on legacy code as well. I mean, there's stuff there that's probably ancient, probably going back to Fortran, whereas Fortran programmers certainly knew about how to take a square root of a number through an algorithm. Now, I don't know much about the code base, but I can assure you the code base has a lot of these historical algorithms in it. Now, granted, there's a ton of them. It's just not one of them. But Wells presents this algorithm. And what number do we get over here? Well, the number they say it is, which is 0.07946. Again, I'm not an expert in how the code base does that, but certainly it's a numerical problem. It's using a numerical technique to get that. Thank you.